All right, 6.4, the central limit theorem. All right, before I go ahead and discuss this notion of the central limit theorem, a little bit of background first. What have we done so far? So from 6.3, we developed the notion of a sampling distribution. And I looked at two of them. We looked at sampling distributions for a mean and for a proportion. That mean is X bar, that proportion is P at. If the notation is a little unusual, just take a look at last night's lecture. This is if you go out and ask a yes or no type of question, a characteristic of some particular group, we can make a proportion or fraction out of it. It can be converted into a percentage really quick. In any case, a sampling distribution for either a mean or a proportion it looks at all possible samples of a given size. And that given size is N. That's your sample size. I did a very simple contrived example to develop the notion of this with some easy to work with numbers in very, very small populations. It's in last night's lecture. It's up on the website. So let's see. A sampling distribution. Now, here's the thing we're going to look at. What are we going to do with that sampling distribution? And I'm going to go ahead and just throw out what we call the central limit theorem. It takes up almost a whole page in your book, but there's a lot of empty space. There's some formulas. Some of them we'll use. Some of them will be built into the process eventually, and it won't worry us overly much as long as we're asking the right questions. So we're looking at the central limit theorem as it applies to the sampling distribution for the mean X bar. In some sense, there's a different central limit theorem for every sample statistic, the mean, the standard deviation, the median, the variance, things of that nature. Different theorem for each one of those objects. A couple of them coincide, and those are the ones we work with. We're working with the one for X bar, and it's the one we work with the most. After that, I suppose it's for the one with P hat. But we look at the one with X bar, and that's where we do all of our major exploration. There are a couple of given requirements. We have a population with a mean and a standard deviation. And we have simple random samples of size n. All right, so there's 1, 2 requirements. Now, part of the issue with the central limit theorem is that it's really broken into 2 pieces. And here's the first part. If n is greater than 30, this is your sample size here. So if n is greater than 30, mu with an X bar, that's the mean of the sampling distribution mu of x bar is going to be the same value as mu of the population. And sigma x bar, that's the standard deviation of the sampling distribution. Sigma x bar is equal to the population standard deviation divided by the square root of the sample size. On the other hand, if n is less than or equal to 30, then the theorem does not apply. Unless the population has a normal distribution. Now, this is really kind of the key to it. And let me try to clarify what I mean by that. Let me bring back the first page. All of this really depends upon the simple random samples and a sample size greater than 30. So the central limit theorem does all of its very good work when and only when, or almost only when, the sample size is greater than 30. It's a real line in the sand. Now, it does not apply if n is less than or equal to 30, unless the population already has a normal distribution. And the outcome of the theory is that the sampling distribution is approximately normal, and here's the big part, regardless of the population distribution. That's a very, very important component of everything that goes on here. That's the upshot of the central limit theorem. So let me show you how this works. And I'm going to do it with a population well, let me show you what we mean by that last little part first. Then I'll get into some very specific examples. You may be saying, huh? So I may have a population that follows a rather odd distribution. Notice that I drew one that was not a normal distribution. Not a normal distribution. Oh no. Here's the thing. The sampling distribution for X bar when x is greater than 30, so here's my value, whatever that value is, that's my value for my sample mean. When I draw in the sampling distribution is going to be normal like that, and it will have a mean with the little x bar, that's my special notation there, equal to the population mean. That's what this says. It doesn't matter the shape of the distribution of the population. The sampling distribution and that would be for x bar. The sampling distribution here is normal. Remember, you're not looking at individual scores here. You're looking at means with n greater than 30. And it's a very important notion. I cannot overstress it enough. Let me put it in with a different color to try to overstress it enough. Normal distribution, regardless of the underlying population distribution. And let me show you how this works for probability distributions. And I'm going to work with the IQ distribution just because I've used that a lot already in my examples. And hopefully you're a little bit familiar and comfortable with it. IQ, we have a mean of 100 and a standard deviation of 15. All right. So I'm going to draw several different pictures here. I'm going to start first with the distribution itself. That's what's going to be here in black. Goes up, comes down. We have a mean of 100. Now what we're going to do is we're going to take samples of different sizes. The first thing I'm going to do is I'm going to take samples of size n equals n equals 9. I know that's nowhere near 30, but that's okay. You're going to see how this is going to work anyway. So samples with n equals 9. Now, before I go ahead and draw that in, I'm going to remind you that this is a probability distribution. That means that the total area is equal to 1. That's what's true for all probability distributions. Now, when I take my samples of n equals 9, that graph would have a tighter standard deviation. The area would still be equal to 1. Now, why is that so? Here's why. The mean stays the same as the mean of the population, but the standard deviation changes as sigma over the square root of n. Now my sample size was 9, so we had 15 divided by the square root of 9. That's 3. 3 goes into 15 5 times. So when we did this guy here, my standard deviation is now 5. It's much smaller. And the area is still equal to 1. It's kind of like everything's been squeezed in to some degree, which sort of pushes the probability for the middle stuff up higher. Kind of like squeezing a balloon. You don't change the volume of air, but you squeeze it here and it pops out there. What if I take bigger samples? What if I take a sample of size n equals 25? So now we're getting closer to that magic number of 30. For n equals 25, this would be even tighter. And again, the area would stay the same because the total area is always equal to 1 under these distributions. Notice here, again, we have the same mean. Mu of x bar is still 100, but our standard deviation is now 15 divided by the square root of 25, or 3. Much smaller. That means the data in general have less spread to the left and to the right, or more concentrated, if you will, here in this middle portion of the distribution. So it's still a normal distribution, but this is the sort of thing that happens as sample size increases. And that's true regardless of the underlying distribution once you get above n equals 30. So for n greater than 30, as I say, starting out with the probability distribution for the variable itself, subsequent values of n make this more and more normal. So as n increases, not more and more normal, normal with a tighter standard deviation. It gets a smaller sigma x bar. The area is still equal to 1. Now, that's what our central limit theorem says. Couple of things. And I'm going to go over some of the basics again tomorrow. We can have two types of questions. We can have a question about an x value in a population, and we can have a question about an x bar value in a sampling distribution. In the first case, z-scores are calculated using the standard way of going about doing things. Down here, it's a little bit different when you're working with the sampling distribution. X bar minus mu sub x divided by sigma of x bar, where you need to remember that that sigma of x bar is sigma divided by the square root of n. Now, fortunately, much of this is already worked into our calculator, so we don't stress about it too much. But there is a part that is not, and that is this part right here, the ability to distinguish between these two types of questions. A question about an x value versus one about an x bar value. And I think that's where I will end this evening. Let me draw one more example. And that'll take us up to our time. And it'll set the stage for reviewing all of this stuff tomorrow night. So, IQ, mean of 100, standard deviation of 15. By the way, it is normal. I'll need that because if some of the questions do require that, another one won't. So here's my question. We random select an individual we want to find the probability IQ is less than 105. Hey, mommy. I'm gonna have to pause this for a second. No, I think it's okay. So what is the probability for an IQ less than 105? So we're looking for the probability someone has an IQ less than 105. Remember, I'm very big on drawing these pictures. There's 100, there's 105. I am interested in this area here. We make the connection between area and probability. All right, so if I'm looking for a probability, I need the normal CDF. In this particular mode, the basic mode, it works with area from the right. Oh, excuse me, it works, yes, from the low and the high, I'm sorry. So now I'll type in negative 10 raised to the 9th. If you saw me do this last night, you understand what I'm doing. Comma. Then we've got, what do I got going on there? Hold on, I got to clear that up. Let me try that again. All right, so negative 10 raised to the 9th, comma, all the way up to 105, comma, mean is 100, comma, standard deviation is 15, close them up, it equals. So 0.63 and change. It's a probability. I want 3 significant digits, 630. The 5 means the 0 becomes a 1, 0.631. So let me stop my sharing and note that this probability that X is less than 105, the IQ of some individual, of 0.631 corresponds to this area in the picture here. Remember, area and probability are the same. So that was a question about an individual. Let me take a look at another question that's very, very similar. What is the probability a random sample or randomly selected sample has a mean less than 105. So the question is fundamentally different. It asks about a mean, but I know there's another normal distribution involved, and this is the sampling distribution x bar. I know the mean of x bar is the same as the mean of my sampling distribution. I know the standard deviation, though, will be different. It'll be sigma divided by the square root of n, 15 over, this time we're going to take a sample of size n equals 9. So that was square root of 9. That gave me a standard deviation of 5. I still have an area. There's 105 right there. I'm still interested in that area there, but my notation's a little bit different. We're looking for the probability that x bar is less than 105. Let me jump back over to my calculator. And back to normal CDF. I still have the negative 10 raised to the 9th. If I'm stuck up in the exponent position, I'll use my arrow key to get away from there, comma, upper level is 105, comma, the mean is still 100, comma, but my standard deviation is now 5. That was 15 divided by the square root. Of 9. And by the way, you can put it in like that. Believe me, you don't always have a perfect square for a sample size. I can actually put in expressions just like that. And now I'm going to get a number that's a little bit bigger than 0.5, but a little bit smaller than 0.63 and change. Oh, I'm sorry. Went the other way. 0.841, my bad. So let me note that, and let me try to explain what just happened. I was thinking backwards. That was my bad. Even better. So let me stop my sharing, come back to my screen. So the probability that x bar is less than 105 corresponds to this area here, just like it did on the other picture. But this time, my area came out to be something much, much different. This time, my area came out to be 0.8. Over here, on the previous one, it was just 0.6. So what's the difference? Why did I get 0.8 and 0.6? What's the difference there? Let me explain what's going on. I'm going to draw, because they're probability distributions, I'm going to draw the two distributions together. I'll try to bring a little bit of scale to the picture. Not much, but a little. All right, so there's the distribution for x, not the sampling distribution, the actual population distribution of the IQ. And we saw that this total area over here to the right, to the left, was 0.631. Now, when we took our sampling distribution, that had a much smaller standard deviation. In fact, let me note what that standard deviation is for this area. It was 15. The sampling distribution has a much tighter hump, if you will, in the middle there. And you can see that much more of that graph falls underneath and to the left of that line there at 105. That line here at 105 did not change. Take a look at what's left in terms of the right tail. A little bit of area right here. That's a tiny bit of area right there. That little bit of area right there is equal to about 841, about a 139. That little bit of area there, 139. And you can see here that this little bit of area here is 369. Anyway, it might be a little bit off on those, but you can see that it's much, much more. Remember, the total area under both of those graphs, regardless of what they are, has got to equal 1. So tomorrow night, what I'll do is I'll run through some more examples here and really try to emphasize and stress the the difference between questions about an individual X value versus the questions about the probability, for example, of a mean or a proportion. So I'm going to stop the recording.